Hi everyone, this is the second lesson from Chapter 6 for Algebra 2A. Technically the title of this lesson is Rational Power Functions, but really I think more of the lesson is focused on just how do we work with exponents, what are the properties of exponents, and a lot of that is review from Algebra 1. Toward the end we do get into what functions look like when they have rational exponents on them in terms of their graphs, but like I said, we're going to start out just by reviewing some things about powers and exponents. So first off, we have this whole list of these properties of the powers and how do we work with powers, because powers kind of follow their own rules. So for example, when I'm multiplying two things together, two powers together, really we're going to end up adding the exponents, because if you think about this, this is like m copies of x, and this is like n copies of x. So if I wrote this all out side by side, the total number of x's would be m plus n. So when we multiply powers, we add the exponents. Usually, that one is pretty intuitive. Usually, most of us know that. This is just to remind you that if I've got two things that are being multiplied together and it's being raised to a power, that power applies to both of those things. So this would become x to the n times y to the n, okay, that power would apply to each of them. Please keep in mind that does not work if there are pluses or minuses inside these parentheses. Then we have to start doing some FOIL and things like that. Okay, when I've got division with exponents, division is the opposite of multiplication, right? So we're going to have the opposite process going on with the exponents. You're going to end up subtracting the exponents here. And that would make sense if you wrote this out, and I mean, you'd probably have to use some actual numbers here. But if I wrote out m copies of x on the top and n copies of x on the bottom, and then went through and crossed them out in pairs, what would be left over is the difference between m and n. Okay, so if I did m minus n, that would tell me how many x's I would have left over. So again, these two properties are kind of opposites of each other. In a similar way, these two properties kind of go together. This is really just saying that if you've got a fraction raised to a power, the power applies to the top and the bottom of the fraction. Now, why can't I just subtract these and make that a 0? Because we just talked about how we're allowed to subtract them. That subtraction only works if your bases are the same. So because these are both x's, that's why I'm allowed to subtract. Here I've got an x and a y, so I'm not allowed to subtract those. Okay, anything to the power of 0 is really just equal to 1. So whether this is a variable or an exponent, whether it's a variable or a constant, like a number, anything to the power of 0 is always equal to 1. Really what that comes from, if x equals 0, that would be a situation like this, where you have the same number of x's on top and bottom. And then they'll all cancel out and you'll be left with just 1 over 1. And then, this is a big one. Do we remember how to work with negative exponents? Negative exponents do not turn numbers negative, okay? Negative exponents do not turn numbers negative. Negative exponents turn things into reciprocals. So this would be the same thing as 1 over x to the power of n, okay? Again, if we go back to this rule here, your quotient rule, this is called, if n was larger than m, and you were to go through and do all of this division, your leftover x's would be down on the bottom of the fraction. That's what's really happening here. Okay, and if you think about it, if n was larger than m, this thing would come out to be negative. Okay, so next up we're going to review rational exponents. So rational exponents are fraction exponents, and we talked a little bit yesterday about working with roots as well, that this fourth root is really like a power of 1/4, okay? And so I'm going to write this kind of the long way to start out with, but then just know that as we move through these examples, you'll be able to do this quicker. So if the fourth root is really like a power of 1/4, I could take this thing and say it's like m to the 6th to the power of 1, whoops, I made the mistake that everybody makes. It's not a power of 4, it's a power of 1/4. And then I can combine these exponents by multiplication, and so this would become m to the power of 6 over 4, which is really just 3 over 2, if I simplify that. Okay, 6 over 4 is the same as 3 over 2. Shorthand-wise, the shorter way to do that is anytime you've got exponents on the inside and roots on the outside, you're always going to stack them in a fraction with the inside number on top and the outside number on bottom. So this is always your denominator of your fraction, and then anything that happens to be on the inside will be in your numerator. So I should be able to just look at this and say, okay, it's 6 over 4, and then reduce my 6 over 4 to 3 over 2. So similarly with that next one, now a couple of things I want to point out on this next one. First of all, you'll notice the 5 is on the outside of the parentheses rather than in here with the G. That shouldn't actually matter. This is really the same thing as this. Okay, that 5 could go on the inside or the outside. It does not make a bit of difference. And then the other thing to remember is that if there's no number written there, that's really a square root. So we're going to imagine there's like a 2 sitting out here for my square root. And then I'm going to stack the fraction just like I did back here. So this would be 5 over 2. And because 5 over 2 doesn't really reduce, that's just it. That's just my answer. Okay, I'm going to leave that there. So now for that next one, I'm kind of bothered by this example because technically 1.2 is rational. So this is a rational exponent the way it's written right now. But if it's trying to get us to write it as a fraction exponent, I just want to take 1.2 and write it as a fraction. Couple of ways you could do that. I look at that and I see that that's a 12 with the 2 in the tenths position. So I think of this 1.2 as 12 over 10, which I then could reduce to 6 over 5. Okay, so I would write this thing as s to the power of 6 over 5. Okay. The other thing you could do in your calculator if you wanted to is you could type in 1.2 and then hit your math button and choose fraction, which is that very first option, and it'll tell you that that fraction is 6 over 5. You know what, let's pretend for this one, because again, I'm annoyed by this one being looped in with these directions here. Let's pretend that this question had actually asked you for this to be in radical form. Meaning it wants you to write it back as a radical, like one of these. Okay, I still would have done these steps. So I need this fraction, and the reason I need this fraction is I need to see what number goes on the outside, what number goes on the inside. Remember, your denominator is always your root. So this would be written as a fifth root of s, and then I'm going to put that 6 in there as an exponent on the s. So this is what this thing would look like in radical form. Okay, so that one I had you kind of go backwards. All right, let's see what else we got. Okay, evaluate these without a calculator. Again, you are going to have a no calculator portion. Excuse me. On your next quiz. Okay, so that 64 to the 2/3, what I would do is I would split that 2/3 into kind of two pieces. I would think of this as 64 to the 1/3, and then with a power of 2 on the outside. Because if I put 1/3 and 2 back together, I would get my 2/3. But these two things work kind of differently. So 64 to the 1/3, remember the question you want to be asking yourself is, what could I raise to the third power to get 64? And my hope is that your mental math is strong enough to be able to just come up with that on your own. If for some reason you can't, you could go off to the side and make a factor tree. But I want you to know that 4 to the third power is equal to 64. So this is really now just saying 4 with that power of 2 on the outside. And 4 squared is 16 for a final answer. So for this next one, and I know you're going to think I'm crazy the way I'm going to write this out, but writing it out this way really gives you a very step-by-step kind of layout. So I want to start with 32 to the 1/5 power. So I'm dealing with that denominator first, and I know I've got a 3 on the outside. The other piece that I haven't dealt with yet is the negative sign. So I'm going to make a separate exponent of just -1. So I've really separated that exponent into 3 pieces, a 1/5, a 3, and a -1. And all three of those do slightly different things, but by writing it out this way, I'm giving myself like a step-by-step guide. I'm going to do this, and then I'm going to do this, and then I'm going to do this. So 32 to the 1/5 power. Remember, the question we're really asking ourselves is what to the 5th power would give me 32? Hopefully you know that that answer is 2, but if not, go off to the side and make a factor tree for 32. So this is going to give me 2 to the 3rd power to the power of -1. Okay, 2 to the 3rd power is 8, so now I have 8 to the -1. And now let's think about what that -1 is going to do. Hint, it is not going to make that a -8. This does not equal -8. Remember, a negative exponent flips things over. So this would be 1/8 as a final answer. Okay, let's do some simplifying. So, and again, these are supposed to be done without a calculator. So when I look at that first one, I'm kind of panicking, right? Because 3 to the 1/5 power, I don't have any way to do that without a calculator. But I could go ahead and put these two things together, right? So if I'm doing 1/5 and then raising to the 10th power, I'm going to multiply those together. So this is really the same thing as 3 to the power of 10/5, which is the same as 3 squared. And we can do that in our head, right? 3 squared is equal to 9. So combine your exponents and then see what happens. This is just checking to see if you remember how to combine these exponents. So if I have x squared times x to the 3rd, that's going to give me x to the 5th power once I add those two things together. And if you weren't sure about that, let's write it out. Here's x squared. Here's x to the 3rd. And so all together, I have 5 x's all multiplied together. Okay, this next one, there's a couple of different ways you could think about it. I'm going to show you 2 of them I can think of off the top of my head. So if I just apply the same rule I did here, I know I'm going to add these exponents together. Now, what I want you to be careful of is I know that these are numbers, right? The 4 and the 4, okay? And so I know you're going to be tempted to either multiply those because there's multiplication here, or you're going to want to add them because we're adding the exponents. But notice that up here, I didn't do anything to the x, right? I didn't like throw in an extra x squared. I didn't make it a 2x to the 5th because there's 2 x's there. It's just giving you the total number of objects, right? So this is saying I have 5 4s on the top, and this is saying I have 5 4s on the bottom. So the 4 is not going to change. So I could think of this as 4 to the power of 0. By following this rule, I would do 5 plus -5 is 0. And then 4 to the 0 power would just be equal to 1. That's one possibility. If I think of this in terms of what negative exponents do, this is saying I would have 4 to the 5th power on the top. This is a negative exponent, so that means I'm going to have 4 to the 5th power on the bottom. And if you have 2 of the same number, one on top and one on bottom, that's automatically going to equal 1. Or you could do 5 minus 5 and you'd get back to this 0. Okay, and that would take you to 1 as well. So either way you think about it, that thing should come out to where everything just cancels and you're left with 1. Okay. So find an equation for the inverse of h. I'm working on example 4 here. So we need to remember how to find inverses. I'm going to think of this as a y. And so to do an inverse, the first thing I'm going to do is switch the x and the y. So x equals y to the 2/3 power. And then if I want y back by itself, I have to think about how to cancel out a 2/3. Well, I would probably raise it to the power of a reciprocal. Sorry, you can't really see that, but that's a 3/2. Okay, so this cancels, and I'd be left with y equals x to the power of 3/2. So as far as these rational functions are concerned, if you're looking for an inverse, it's really just going to be the reciprocal of the fraction. Is this a function? Yeah. I mean, when you plug your x numbers in, you're only going to get one y value out, correct? And I mean, this is just another function that looks like this one. It's a rational power function. So I would say yes. By the way, we can also look at it on a graph, which we're going to do in just a second, and use like the vertical line test or the horizontal line test. Okay, graph H and its inverse on this scale. I'm going to pull up a Desmos graph to do that with you real quick. We'll take a look at both of those. This is just telling you how to set your window. So from -1 to 11, I don't know why they chose 11 instead of 10, but and then -1 to 10 for your y-axis. And we'll look at them and we will verify that these two things are inverses of each other. Example 4. From the notes from 6.2, the original function was y equals x to the 2/3 power. And this is what that graph looks like. Now, I want you to notice this graph has two sides to it, right? It's symmetric over the y-axis. However, when we're dealing with rational power functions, we never consider that the domain could include negative numbers, even if the graph says that it could, okay? There's lots of reasons for that. And we're going to talk about that more probably in this first homework assignment. We're going to kind of explore the reasoning behind that. But as far as a domain goes, we always restrict the domain to just the positive numbers. So all real numbers greater than or equal to 0, meaning we're going to kind of ignore this left side of the graph when it shows up. And like I said, there's an example in the homework that does a beautiful job of explaining why that happens. So we're going to do a further discussion, I think, once we explore that homework problem. So just wanted you to know why I'm kind of just focused in on the first quadrant here. I'm kind of ignoring the left side of this graph. That's intentional. And then the inverse we came up with is this y equals x to the 3/2 power. And so the purpose here is we want to just verify that these two things are inverses of each other. Remember that inverses are always reflections over the line y equals x. And so if you look at that purple line, if we were to fold it in half on that purple line, the blue line would land right on top of the red line. So these two things are, in fact, inverses of each other. Okay, I think that's about it for today. Like I said, there are going to be some concepts that you explore more through your homework assignment, and then we'll discuss those in class when I see you again next time. All right, have a great day.